Okay, I guess we're ready to go. And again, please interrupt anytime you have any questions. Goes a lot better with if you're helping me out in case I run off the page. So the first question that had several check marks on it is number 7 in related rates. I guess before I start that problem, I should just review like what are the two different word problems that we're focusing on in section 4.2 and 3. Related rates, basically you get some function of the x variables, the x's and y's, is equal to some other function of the y's and z's, that sort of thing. And then with related rates, I'm just going to, this is the relation between the x variables and the y variables, and I figure out the rates by just hitting d dt on both sides of the equation. And then that will give me a rate of, thanks to the chain rule, I'll get a dx dt will pop out in front of everything. And you'll get a dy dt that will pop out of the chain rule of all these. And then so I just have now related the rates that we were focusing on. And so that's when we're trying to find a solution of, well, if this one's moving this fast, well, how fast is this one moving? And now the rates are related, so I can solve the equation. And then with 4.3, again, we're just using calculus. We're going to take derivative somehow, but we're trying to find the max of some function of whatever variable you want. And to find the maximum of the variable, you just find where x makes the derivative equal to 0. So we find the thing we're trying to maximize or minimize or optimize. And we're trying to find the variable that makes the function maximized. And so that's when the function's derivative is 0, is where it's at the top. Or if we're trying to minimize it, then we're trying to find where the derivative is 0 at the bottom. Okay, then you're going to use your first or second derivative test. Okay, so those are our two general tricks here. We're always just taking the derivative at some point. And so for section 4.2, the first problem is number 7. Let's see what that says. So I'm assuming you can read along the problem, so I don't have to write it down here. We have this airplane flying over at, let's see, 500 miles per hour is our airplane. And it's more like a fish, but the airplane zooming along at 500 miles per hour overhead. And we've got us sitting down here and watching it. And we're in an anti-aircraft gun. So we're going to try to shoot this airplane down. And we're watching as the airplane is moving at 500 miles per hour. And we keep an eye on it. And then we're going to use this anti-aircraft gun to shoot at the airplane maybe. But I don't know, we're just watching it. And so the question is, how fast do we have to rotate the gun in order to keep a trained eye on the airplane, to keep a line of sight on it? And so the question is, how fast do I rotate it? In other words, how fast do I have to be able to change the angle as it rotates around, as the airplane zooms that way? And so in order to figure that out, we're going to have to find some way to relate this rate. I'll call this one the x variable here. And 500 miles per hour will be how fast the x changes, how fast this distance changes. So really what x is the distance across the land from our place to where the person would be, or where the plane would be, if the plane was right on the ground. And then what we're looking at for the angle that changes here is that this angle, theta, changes from when it's farther away, the angle is small. When it's closer up, the angle is going to be larger. When it's directly overhead, the angle will be 90 degrees, and then it'll go to be a further angle, greater than 90 degrees, or pi over 2 in radians. Okay, so, but I want to know exactly how is this angle changing as time goes by? I know dx dt is 500. So I know that rate. I want to relate that rate to our question, which is how fast is the angle changing? So that's our goal, is to try to find d theta dt. Well, so I have to relate this rate to this rate somehow. So I'll first have to relate those two variables. So you want to simplify your picture here at some point and realize that your angle theta is relating your x variable to this piece right here. And so I need something else on this triangle. I either need to know the distance to the plane, which changes all the time, or else I need to know this side of the triangle. And we do know this side of the triangle. It's given in the problem that the airplane is flying at an altitude of, I don't know, what is it, 10,000 feet, 1,000 feet, 10,000 feet. Okay. So this is going at 10,000 feet. So that's this piece right here. This opposite side is 10,000 feet. So now I also know the distance from my viewing box here to the airplane is the hypotenuse, which can be solved by Pythagoras' theorem. But we don't know, or we don't care rather, how far away it is. I just care about theta. Okay, and as far as theta is concerned, two sides is enough to figure out how to relate theta to the two sides. And so the one we're going to use on that one is for this right triangle, we have the opposite over the adjacent. And so that's the tangent function. The tangent of our angle is the opposite over the adjacent, and that's it. Now that's the hard part, because now the rest is math. It's just anything a computer can do. We've related the two variables. X is related to theta. So theta here is related to x. Those are the two things we care about. We're looking for, we know dx dt, we're looking for d theta dt. So what we do is we now differentiate both sides of the equation with respect to t. So at this point, I just want to hit d dt on both sides, and that's the rest of the game. Now the rest is just use your calculus. Okay, and in particular, we're using implicit differentiation in some sense. We're using the chain rule, that theta is actually a function of t, an unknown function of t, but it's really a function of t, so I have a function of t. So when I differentiate it, I differentiate the outside function, secant squared. I leave the inside function alone, I don't touch it. It's just theta of t still, I just don't know what it is, but it is what it is. And then I have to multiply by the derivative of the inside function. And again, I don't know what that is, but whatever it is, here's the derivative of this function. And now I have to differentiate this function. And again, x is some function of t. And so I need to differentiate with respect to t, a 10,000 x to the minus 1 power is just a little bit easier to differentiate than I do on the quotient rule or something like that. So I'm going to go minus 10,000. As the minus 1 comes down, I still have x to the minus 2. And that would be the derivative with respect to x, but I'm actually differentiating with respect to t, and x is a function of t. So I have the chain rule in here. This is a function of t to a function to the minus 1 power. And so I have minus 10,000 x to the minus 2. I still have to multiply by the derivative of the inside. Okay, so that's the crucial pieces, is that I now have the rate of the angle related to the rate of the distance here that we're traveling. And we already were given that the distance changes at a constant rate of 500 miles per hour. And so now I have theta. So I'm done. I have d theta dt equals, now I just solve for it. I get divided by secant squared. Or really, I should remember that secant squared is 1 divided by the cosine squared. So secant of theta equals 1 divided by the cosine of theta. So that fact, I'm going to stick that in here, and I'm going to do it in my head, and I'm going to move this is 1 divided by cosine squared of theta. So I multiply both sides by cosine squared of theta, and I'll have d theta dt. So I just multiply both sides by cosine squared of theta. And so I have cosine squared of theta. I have x to the minus 2 here, which I'll just put down here. And I have dx dt. Now that's it. That was the question. What's d theta dt? How fast is it changing? That's the answer. But I have a whole bunch of variables over here. I'd like to have a number. Like how fast is it changing? And the question is, number 7 has 3 different places. Like what happens when it's a mile away? What happens when it's 1/5 of a mile away? What happens when it's directly overhead? So that's the answer. But part A asks a more specific question. How fast, what's d theta dt when, how far away when the plane is 1 mile away? So when the plane is 1 mile away, how far is this, how fast is the rangefinder having to rotate? And well, the situation is I have this big messy formula, and it actually has a bit of a problem. Remember, dx dt is 500 miles per hour. Okay, and so we just have a bit of an issue of like, we also have the, oh, okay, I guess it's in miles per hour, so we don't actually have an issue. The next question is going to ask when it's in feet. Okay, so they're just going to ask you to change it to feet. So if x is 1 mile, I just put in 1 here. I have cosine of theta. I have dx dt is 500 miles per hour. So we have d theta dt equals minus 10,000. I have to have cosine squared of theta, which I don't know yet. I'm putting in the 1 for x squared, so it's 1 mile squared, 1 squared, 1 mile squared. And then I have dx dt is going to be 500 miles per hour. And so we have our d theta dt in terms of all of these. The only issue is that I don't know what theta is. Okay, so when I am 1 mile away and I am 10,000 feet above, well, what does that even look like? Is this rectangle approximately correct? Or sorry, this triangle, is this approximately correct? Well, what is a 1 mile compared to 10,000 feet? And we need to know that. Well, 1 mile is 5,280 feet. So no, this triangle is not accurate, but it gets the idea across that I just have theta related to these 2 different pieces, and I can figure out what the angle theta is if I know what the sides of the triangle are. I know that theta is the inverse tangent of 10,000 divided by 5,280.
Can you move it down a little bit, please?
Oh, yep, thanks. Okay, so when we have this situation, we now know what the theta is, so I can figure out what the cosine squared of theta is. I actually really just want to know what the cosine of theta is, right? So I really want to know the cosine squared of theta. So I don't really want to know what theta is. That's, if I wanted to know what the angle was, that would tell me. But I really want to know, to figure out d theta dt, I need to know cosine of theta. And the cosine of theta is adjacent divided by the hypotenuse. So what I really have to do is figure out what the hypotenuse is. And that divided by that, when I square it, will work. And so it is just, the hypotenuse will be the square root of this squared plus this squared, and that'll be it. So it's the square root of 1 mile squared plus 10,000 feet is 10,000 feet divided by 5,280 miles. So 1 mile per feet is 5,280. And so if I have 10,000 feet, it cancels with this, and I just have around 2 miles. So it's about 2 miles high is 10,000 feet, because 5,000 feet is approximately a mile. And so it's a little more than, or a little less than 2 miles, but just for simplicity, so you're going to put that number in here and square it. And so that's what you need to do to calculate this. So the cosine squared of theta, just to finish this off a little bit. Oh, and I have minus 10,000, which I'm not happy about. We have it in miles and miles per hour. So I need to change the 10,000 to miles, and minus 10,000 feet. So I divide by 5,280 feet per mile. 1 mile per 5,280 feet is just 1. That's just one thing. So I can just throw that on. And then minus the 10,000 feet, they cancel the feet, and I just have minus around 2 miles is what we get here. And now the cosine squared of theta is in terms of miles, it's just this piece is adjacent divided by hypotenuse. It's 1 divided by square root of 1 squared plus this whole thing squared. Has to be put in there. And I don't want to write that out. It's too messy for this presentation. I've already got this huge, long bit of information. I don't have a blackboard. Okay, so that's the cosine piece right there. And now I still just have times 500 miles per hour. And then all the pieces cancel. I have a mile here, I have a mile squared here, and I have a mile here. So all the distance terms disappear if I do all that, and I'm just left with per hours. Well, what's per hours? And that's what radians are. Radians are these unitless units. So I just have angles per hour. Okay, radians per hour is what's left. And so that whole thing, once we calculate it, gives us our answer. Okay, are there any questions about that one? So it has got some nitpicky arithmetic in here to keep track of. And the trigonometry has to guide you in figuring this all out. You have to already have memorized that the cosine is the adjacent over the hypotenuse. You have to memorize that the Pythagorean theorem says that the hypotenuse squared is equal to the 2 different sides squared added together. So you have to be able to do those calculations over and over and over again. Trigonometry is one of the best, most useful applications in any situation. It never disappears, so it's fundamental. Okay, so that's it. And then it also asks, like, what happens if it's 1/5 of a mile away? So be 1/5 of a mile away, and so you're just going to, when you're asking 1/5 of a mile away, you're just going to put 1/5 in where the 1 showed up here. It's now the adjacent leg of the right triangle. And same thing with the last one. And then people also asked about number 8. And number 8 is just same problem with feet. Okay, and so it asks if it's moving at 500 miles per hour again, and it changed, the only thing it changed to, same, it changed to feet, it changed to 100 feet high, I guess. Elevation. So you're just going to change that 10,000 feet to 100 feet. So same problem. And then the only difference is that they also talk about it being when x is, when it's 1,000 feet away. that sort of thing. And so the whole thing is a matter of converting from miles to feet. So if you still have this thing moving at 500 miles per hour, you have to make sure that everything is in the same units. And so just remember that 1 mile is the same thing as 5,280 feet. And then you're good to go. So just know that 1 mile equals 5,280 feet, which means that 1 equals 5,280 feet per mile. So I can always put 5,280 feet per mile into any calculation. And I can put a foot and a mile up here, and then I can cancel the feet. And so we do that all the time. So that's really a science trick. Science is, in my experience, science is half of doing this. It's called dimensional analysis, making sure that your dimensions are straight, that your feet versus miles, that you don't mix up feet and miles in one equation without keeping track of the details. And so you're really going to get a lot more of that when you take any science class, because science is just applied math, right? Okay, and any questions about that one? That's probably the trickiest one of today, the one with the most questions.
Yep. Just about the C's for the 7 and 8. Were you supposed to like take the limits of those?
Oh, good question. Yeah. Okay, so let's finish this problem with part C is asking what happens when it's directly overhead. So what happens when the plane is actually keeps moving and this angle gets all the way to here, then all of a sudden the triangle doesn't make sense anymore. When this is directly overhead, then the triangle becomes just a straight line. Right, the x equals 0 then. The distance from the base to where the plane's footprint is on the ground is 0. And so I'm just looking directly overhead. It's no longer a triangle. Well, the trigonometry still works. We are just talking about the unit circle when we do this. And that's just up here instead of that angle. When theta equals 90 degrees or pi over 2, we are still working with the same thing. So all the equations still work. It's still true that the tangent of theta and all this stuff works. It's still true that that d theta dt looks like this. But now the question becomes, well, what happens as x goes to 0? We have, as x approaches 0, I'm dividing by 0 squared. So the equation doesn't really work at the moment when x equals 0, but it works at every moment up to the instant when x equals 0. There's still a triangle right before that, even though it's a really, really skinny triangle. So the question is, well, what's the limit as x goes to 0 of this situation? And theta is still just in terms of x. And so let's finish this off one more time. I'll recopy this on another piece of paper. And we'll sort of analyze this a little more carefully as the x goes to 0. So we've got here that our x is going to go down to 0. And there we're still wondering what's theta doing as this is happening. Got this awkward 10,000 up here. And as x goes to 0, what's our term? And so what we're trying to figure out is what's d theta dt as x goes to 0. And I guess I should have mentioned that back here of what's the intuition behind this. Back from the very beginning, when my theta is kind of small, that means the plane is far away. The plane is constantly moving overhead. But my angle, theta, is going to change as time goes by. You got to ask yourself, is the angle that I'm looking at it, is it changing more when it's far away, or is it changing more when it's directly overhead? And I think our intuition should be pretty clear on that, that when it's far away, I'm just barely moving my eyes. It's just slowly coming in. But when it gets real close, as it continues to move, my eyes really have to rotate. I have to really rotate my head as the plane moves directly over me. So that's the fastest I'm ever going to rotate. And the question is, well, do I have to rotate at 500 miles an hour? Well, no. I mean, I just have to rotate my eyes a little bit as the plane goes by. But this is the fastest I'm going to rotate. And exactly how fast is that? What is d theta dt as the plane is zooming over? And so that's what this equation will answer. We had this equation. We solved that it's d theta dt is minus 10,000 cosine squared of theta divided by x squared times dx dt. Okay, and so I just want to write this down a little more carefully, that cosine squared of theta is this side divided by this side squared. So we know that the cosine of theta equals the adjacent divided by the hypotenuse. Okay, so, and the adjacent happens to be the x. The hypotenuse is this other piece that we can figure out with the Pythagorean theorem. Again, I know that x squared plus 10,000 squared, I'm getting tired of 10,000. 10,000 is 10 to the 4th power. There's 4 zeros in it. So when I square that, it's just going to be 10 to the 8th. And I don't have to write down 8 zeros. I can just write down a single symbol there. Okay, and so now I know x squared plus 10 to the 8th has to equal this side squared. So this side has to equal the square root, the length has to be the square root of this squared plus this squared. And 10 to the 4th squared is 10 to the 8th. Okay, so that's the hypotenuse thanks to the Pythagorean theorem. Again, skipping a one step of algebra, right? And so now the cosine of theta is x divided by the hypotenuse. So it's x divided by the square root of x squared plus 10 to the 8th. Okay, that is going to go in for cosine squared. I needed to square this to get the answer. So therefore we know that d theta dt is minus 10,000, 10 to the 4th, tired of that again. Cosine squared is going to be this squared is x squared over the square root. This disappears. And then I have to, so that's just the cosine squared. Okay, that's just the cosine squared. I also have to divide by x squared and put the dx dt. So that part is just the cosine. And I have to square it. And so that's what our problem looks like. So now simplify the algebra is just x squared divided by x squared. Those disappear. And so I just have this cute enough problem. I have d theta dt equals minus 10 to the 4th divided by x squared plus 10 to the 8th. And I still have the dx dt. And we know what the dx dt, it's constant. We're always just doing 500 miles per hour. Okay, so this is our d theta dt. And so now the question is, what happens as x goes to 0? So d theta dt at x equals 0 is equal to the limit as x goes to 0 of d theta dt. Okay, equals the limit as x goes to 0.
Can you move it down again, please?
Oh, thank you. Appreciate it. Okay, so my d theta dt, I'm trying to figure out what's d theta dt when x equals 0. When x was equal to 0, when this representation of d theta dt, we have, I'm dividing by 0. But what happened when I stuck in cosine squared has an x squared in it. And so the x squared and the x squared cancels. And so now when I stick in x equals 0, there's not a problem. I'm going to be able to stick in x equals 0. So it's really the limit as x goes to 0 of this formula up here, but the x squared's canceled, and so we just have this. We just have minus 10 to the 4th over x squared plus 10 to the 8th times 500. And if I was a little cleverer than I am, I would have taken those two zeros and put them in x to the 6th power with a 5. So I'll do that last, is minus 5 times 10 to the 6th power, just 5 with 6 zeros after it. And then divided by, x goes to 0, that one's 0, divided by 10 to the 8th. Okay. And, well,
I have a question about the 500. It seems like if it's moving towards your object, it's supposed to be negative, right?
oh yeah, that's a good point. That's a perfectly excellent point. I missed that the entire time, right? So all the way through, I was supposed to put the 500 as a negative. So dx dt was actually shrinking. And so since that's decreasing, it's the rate of change, dx dt, is not positive 500. That would mean that dx, or that x, is increasing if it was positive 500. The entire time I've done it wrong. I don't have another color here to change that. So I don't know. I don't want to just scratch everything through, but I should have had a minus here. Okay, so I need a minus there. I needed minuses everywhere I saw. I put in a 500 for dx dt in the last problem, right? And so on this one, I really need a minus 500 all the way through there. And so when I put the minus on the minus, I'm actually going to get a plus here to get my terms. So that's what that happens all the time in science. People just get so comfortable with that mistake. So I'm not remotely apologizing for it, because I mean, I should apologize, but nobody's perfect, and I'm just really happy and comfortable making mistakes all the time. That's why I'm a mathematician, is because I'm human and I'm allowed to just keep making mistakes. And so scientists are just constantly, they ask, like, they don't care about the sign at the end. They assume they've made 3 or 4 sign mistakes during the course of a long calculation. And so at the very end, they just check to see if this solution makes any sense. Is how is the theta changing? And when we were looking at our problem in the beginning, we should already ask, is d theta dt positive or is it negative? In other words, is the angle increasing or is it decreasing? So when I'm looking at the plane and it's coming towards me, is the angle getting larger or is the angle getting smaller? And it's obviously getting larger. So it's increasing until I get to 90 degrees. So the derivative of the angle should be positive with respect to time. Okay, so at the end, when I got this negative number, if I'd have thought about it for 1 second, I'd have known, that's the wrong sign. And you go back and check these things. So good catch. D theta dt should be, or sorry, dx dt should be negative, so that the d theta dt is positive. Okay, that's the sort of autopsy you do on a problem after you're done, is like, check to see you've got the solution here. What was wrong with your process? Okay, and that's what scientists really focus on, is also now, what's the units? Is this per hour, per second? What is this, feet, miles, or is it radians? Okay, so all these different things you need to make sure is correct afterwards. But in this class, I'm really concerned about the math, right? And so I'm spending all my time focusing on, the trigonometry formulas. How do I actually calculate these things? And then I'm concerned about the limits, so the calculus, what's going on. And so that's what we really focus on. When you get to a science class, they just take the math for granted. They do that all in their head mostly. Okay, and so they just zoom through it and they just keep track of the units. And so a science class is always very different than a math class. Math is like elementary science. Okay. And the good scientists know that math is the easy part. The bad scientists didn't learn that easy part, and so they're not very good at it. And so they're not very good scientists. Okay, any other questions about that whole thing? So that's how we can find d theta dt at the maximum spot. when x equals 0. Okay, well then that's the major one, 7 and 8. Then we have 9, 10, and so all the rest are don't have extra check marks on them. But yeah, I'll spend the rest of the time on those. But let's jump to the section 4.3, I think. 9 is a really good one. 10 is a good one here on this section. So they're all good. So I might just go a lot faster after doing one from section 4.3 a little slower. Then I'll go through some very, very fast, so you can stop and pull back the video. So let's do one slow from section 4.3 and then go back. So I don't know which one. So none of them were asked. Let's see, 9. Soda can's a good one. So we need a cylinder, optimizing the amount of material we're going to use. Then 13, power line to an offshore facility. So 13 we did in the lecture last time with different units. So you can go back and check that one. But it's very much like 16 where a dog throws a stick in a lake. So I mentioned that too. So let's really do the soda can right now. And if you want to know more about 13 and 16, so in section 4.3, number 13 and 16, refer back to last week's lecture on it was the power station with the offshore facility. The question is, how far along the coast should I move the power line before I shoot off and go underwater? And should I just go all the way to the end and do the water, or should I go straight water the whole time, or should I go the Goldilocks solution half and half? And so I went through that very slowly and carefully. And so it's the same problem in both 13 and 16. But so this week, let's do a new one of the soda can, number 9. So, but go back and review this, the way I did this problem, and just change the numbers, and that gives you the solution to these two problems. Okay, so for number 9, I'll jump to a new piece of paper. That we have this standard soda can, roughly, so we're on page 187, if you're trying to follow along in the book. So we have this soda pop can, and we have that it's going to have a volume of 206 cubic inches. So we're going to do all these things in inches for some reason.
It was a different volume actually for number 9. Say again? It's a different volume for number 9.
Oh, okay. What was I looking at? Number 10 apparently. It was 206. Okay, so we want 355. That was number 10. So volume is now 355 cubic inches. So a little larger soda can, and it has that much liquid in it. So that's its volume. And we're trying to figure out, well, what shape should we make the can? To get 355 cubic inches, I can make a really long, tall can. I can make a really short, fat can, or I can make some sort of Goldilocks somewhere in between. Now, there's a reason that we have our cans the size they are. First of all, they fit our hands, but nicely. But and also we like the certain amount of volume before we're sick of the soda. But also I could make it really tall and skinny. I could make it really wide and fat. Why do we do it the particular way we do? It's surprisingly close to the ideal spot to minimize the aluminum. used. Okay, that's our goal here, is I want to pick which one of these has less aluminum when I make it. If I make, so which one do you think is the smallest amount of aluminum? Well, if I make it too tall and skinny, I mean, I could make it even taller and skinnier. I could make this thing, well, infinitely tall if I wanted to. And it turns out that would be an infinite amount of aluminum if I was going to stick the same volume in a really, really skinny can, or I could make it incredibly wide, long, and super flat. And that would be the same volume, but that's an enormous amount of aluminum I'd need to use. Okay, so the ideal Goldilocks perfect can here we're looking for is to find the minimum amount of aluminum used. And so, well, I have to decide on two different things: how wide it is and how tall it is. So is it this wide and this tall, or is it only this wide and this tall, or somewhere in between? So what I need to do is I need to figure out the height of the can, and if you figure out the diameter of the can. Our equations are actually sort of, we memorize the equations in terms of the radius. So instead of the width of the can, we'll do the radius of the can. If I choose the radius, it tells us our width. If I choose the height, it tells us our height. So those two variables will tell us the volume. And so the minimize the aluminum used is the surface area. So I want to minimize the surface area. And so we need to figure out what the formula is for the surface area in terms of the radius and the height. And so what is the surface area? Well, we've got the surface area of the top, and that's pi r squared. Surface area of the bottom is another pi r squared. So I have 2 pi r squared surface area so far. And the surface area of the surrounding area here is just, if I cut these off and I unwrap them, then it looks like this. If I slice it down the middle and I unwrap them, and then I spread that all apart, and I completely unwrap it, then we're really just talking about same height of a rectangle that has been wrapped around the can, right? And I had the same height as we had before. And now what's the width of the whole can? Well, it's just the circumference of the circle here. And so it's just 2 pi r. The height's the height and the length is 2 pi r. So the area here is 2 pi r h. Okay, so now I have to add on 2 pi r h for the side, and then pi r squared and pi r squared to get the surface area. Surface area is 2 pi r h plus 2 pi r squared. Okay, so that's what I'm trying to minimize. I want to find the minimum surface area. And so I need to choose the r and the h that makes this a minimum. Well, if I choose r is 0 and h is 0, that's a minimum. That's 0. That's good. Well, that's not very good. I have a constraint. So it's subject to the constraint that I need my volume to be 355 cubic inches. I am not wanting to minimize the surface area of an infinitely small can. I want to minimize the surface area of a can that can actually hold the amount of volume I require to sell. Okay, and so subject to the constraint is that the volume equals 355 cubic inches, and the volume is just the surface area times the height. So that's how we do volume, is just the base times the height, right? So the base area is pi r squared, and the height is the height. Okay, so this is our constraint, and this is what we're trying to minimize. So if I pick my r real small, then my h will actually be really big, because if I pick my r small, then to keep this 355, I have pi divided by the small r, and I'll get a big height. And so if I make my r too small, the height gets big. Okay, and if I make my height real small, then my radius gets big. And that's what this constraint says, is if I make my height small, according to the squat fat can, then my radius, if my height is small, then my radius grows. And that's this formula says if h is small, then the radius is equal to 355 divided by h divided by pi square root. Anyway, when I divide it by small, I get large. So this constraint forces this to only be a function of one variable. If I change one variable, the other one is forced to change into a certain way. And so that's what I'm going to do with this is I have this constraint. I can solve for the easier one to solve for. I'm going to solve for h because the r has got a square root in it if I solve for the r. And then I'm going to stick that h in right there. And then I'll have a function that I'm trying to minimize in terms of one variable. So that's the goal. Let me recopy that things that I've scratched up over there. I'm trying to minimize the surface area, which is 2 pi r h plus 2 pi r squared. Subject to the constraint is that the volume is 355 equals pi r squared h. Okay, so now I'm going to solve for this h right here in terms of the r, and I get 355 divided by pi r squared. I put that in right there, and so that gives me my surface area that I'm trying to minimize is 2 pi r times h, which is 355 divided by pi r squared. And the pi is going to cancel, one of the r's is going to cancel, and that's just part of the surface area. I also have to have 2 pi r squared. And so that's our function that we're trying to simplify. So this is just a function of r. If I change my r, my surface area changes. And the question is, when is this thing a minimum? When does it have a minimum value surface area? It has a minimum value surface area when the derivative is 0. But it'll be at the very bottom of what's possible. So I'm going to take the derivative of this with respect to r, set that equal to 0, set the derivative equal to 0, and solve for what's the radius that's perfect? What's the radius that minimizes the surface area? Okay, so before I differentiate this thing, I'm going to simplify it a little bit. So f of r equals, my surface area is f of r, is get rid of the pi. I have 2 times 355 is 710. And then I have pi's cancel and I have r cancels. And I just have this r cancel this r. I get r to the minus 1 power that I want to do because we're in calculus, right? Easier to differentiate. Plus 2 pi r squared. Okay. There we go. And so now it's easy because now it's just math. All that other stuff, that's the science, right? Is the modeling the reality with some sort of math formula. So once you get down to math formulas, then a computer can do it. So this is the easy part. So that's my pitch to stay away from science, just only do math because that's the easy thing. So if you like word problems, then go into science and make actual money and be an engineer. But then you're going to be in trouble with all the difficulties. So okay, here we go. Try to find. So I want to try to find when is this a minimum, and so I'm going to take the derivative with respect to r. Maybe I shouldn't use that notation because we were just talking related rates. Am I differentiating with respect to t? No, I'm differentiating with respect to r. Okay, and we just have now minus 710 r to the minus 2, and that's it. No dr dt, right? I'm not differentiating with respect to t, I'm differentiating with respect to r. Plus now 4 pi r, and that's our derivative. Now I'm going to set that equal to 0 and solve for r. Okay, so I need to find what's the r that makes this 0. Okay, well, simple algebra here. I'm going to move this one over to the other side and multiply by r squared. So when I do that, I get 4 pi r cubed on this side. When I multiply everything by r squared, I get r cubed here. and the 710 on the other side becomes positive, and then I multiplied that by r squared, so we're done. So two steps of algebra gets us here, and now I just have r in terms of a number, so r cubed equals 710 divided by 4 pi. That's r cubed, and if I cube root both sides, then that's our answer. So that's the only possibility of what could be a minimum. Now you really want to analyze this a little more carefully using what we did, first derivative test or second derivative test, to find out, is that really a local minimum? And then that's a possibility. Then the other thing you want to do is find out, is there any other possibility for what could be a minimum? Is there any place else that we could get? This is the only place where the derivative is 0 or doesn't exist. So the derivative always exists except at r equals 0. And so the only possibilities for where I can get a minimum is here or the endpoints. And so what are the endpoints is our question. R equals what? What is the worst R can be? What is the limits of it? And basically R could equal 0 is the smallest it could possibly be. But remember, what does radius 0 mean? It basically means as the radius shrinks down to 0, we're talking about this picture. As the radius shrinks to 0, this thing gets infinitely long. Okay, now technically you'd have to check that one to make sure it's true, but I'm not going to do that. Okay, we're in a practical problem. I'm not going to do the limits right now, but that's why we study limits. One of the many reasons we study limits. Okay, and the other possibility for R, well, what's the largest R could be? So we found that this is a nice number. There's a possibility in between. R equals 0, and what's the largest R could be? Well, how big can I make it? Well, if R is bigger, then we get bigger and bigger and bigger. I get a larger and larger can, but the volume can still stay at 355 while the height shrinks to 0. And so the radius can grow to be an enormous can. And theoretically, there's no limit to how large R could be. So these are our endpoints. 0 to infinity, no endpoint here. And 0 is the smallest. Nope, nope. Okay, those are not minimizing the surface area. And so this is our solution that will give the minimum surface area. And so what is the solution? The surface area that's minimum is f of that particular R. So plug that particular R back into our equation for surface area, and then we're done. Okay, any questions about that? That we plug that all back in and we're good to go. I'm not doing the calculation here. So. Okay, so that's hours worth of homework. Are there any ones in particular that you want me to go through quickly? I'll go through them a lot faster. I slowly explained the thinking behind why you do it this time. But if I do any more, I'd be happy to just do them without explaining them so carefully.
On page 179, number 14, it says, I think the woman is 5 feet tall. Does that affect our calculations?
Yeah. So they're talking about her sight line. So if she's 5 feet tall, I guess they're being nitpicky about the 5 feet, that you want to assume what's the height of the balloon. So you need to keep in track her height. Now, since they're being nitpicky about that, I don't know, since they say her sight line, I'd be extra nitpicky and say, okay, well, her eyes are 6 feet or 6 inches below her scalp too. I don't know what about her hairstyle? Okay, it's silly. Okay, so if you're going to worry about the 5 feet, you should worry about it since they put it in there, but I would not be nitpicky about that in a math test. So I'd
Sounds good.
either answer you gave me, I'd be like, yeah, whatever, if you're using the process correctly. So that's the big lesson. Tomorrow I'm going to do our last lecture, but the first part of the lecture is going to be on the midterm, or sorry, on the final exam and what's on it. And so I'll tell you everything that's happening. And that's that's it. So anything else? Okay. Well, thanks a lot. If there's no other questions, I won't do any more problems. Anybody want me to see anything else? Okay, well, I'm canceling the live YouTube then.